Remember from our previous screencast that diastereomers and stereoisomers, diastereomers are stereoisomers that are not mirror images of each other. So diastereomers are stereoisomers that are not mirror images of each other. Right? So to be stereoisomers, they must be different molecules that have the same molecular formula and the same connectivity. One way that a molecule can be a diastereomer is to have different configurations around a double bond. So they can be diastereomers if they have different configurations around a double bond. And so, for example, if we look here, we have cis-trans isomers. These have different configurations around the double bond, so that means they're diastereomers of each other. So when we talk about diastereomers, if something is a cis-trans isomer, by definition, these are diastereomers of each other. Now, we haven't talked about how to name these yet, but we need to, so let's look at how to name these. Because the double bond configurations can distinguish diastereomers, we need to characterize the absolute configurations of double bonds in a way similar to how we used R or S. Now, I really want to point out here, RS, that's for a carbon with 4 single bonds. E and Z, only for double bonds. So, to determine the configuration around the double bond, you need to first determine which of the 2 substituents on each alkene carbon has the higher priority. So you need to determine which of the 2 substituents on each alkene carbon has the higher priority. Okay, and then once you do that, you need to assign either an E or Z configuration. And one of the things I want to point out is when we are determining priority, it's the same way that we did that with R and S, right? The higher the atomic number, the higher the priority. But what we're doing is we're comparing the ones on the same carbon. So this one is compared to this one. And then over here, this one is compared to this one, okay, to determine what's high priority. What you're going to see is that the high priority groups are on the same side of the double bond. That's the Z configuration. And if they're on opposite sides, that's the E configuration, which I actually had another slide for that. So I got ahead of myself, right? So if the high priority, I'm going to say HP, are on the same side, that's the Z configuration, right? And so we're Z here, that's the German word zusammen, which means together. That's where the Z comes from. And then if the high priority are on opposite sides, that's the E configuration, right? And that means, that comes from the German word entgegen, which means opposed. All right. Now, here is how I remember it. I love alliteration. And so Z, right, is the same or same side. The other way that I remember this is the E configuration is on opposite sides. right? And so I want you to notice there's a consonant here and a consonant here and a vowel here and a vowel here. So the vowels go together and the consonants go together. If that works for you, that's great. If it doesn't, just ignore that. So I want us to look at some examples of this. Now we're going to use all the rules that we've learned so far as high priority is concerned. So when we compare CH3 to H, CH3 is going to have the higher priority. And when we compare chlorine to CH2, chlorine is going to have the higher priority. So the two high priorities here are on the same side, so they get the Z designation. And the way that you do this is you put the Z out in front with parentheses, very similar to R and S. And then here we can see they're on opposite sides. And you can see the E here. And of course, these two things are diastereomers of each other. Now, when we have multiples, so let's say you have multiple double bonds, that's, you would use the location of the double bond with the Z or the E as well. Okay, and so that's what we'll see there. Now, diastereomers don't necessarily have to have a double bond. So let's look at an example like that. So when we look here, okay, we have these two molecules, they're diastereomers of each other. The two structures are going to have the same molecular formula and the same connectivity, but they're different molecules, but they're not mirror images of each other either, okay? And so if we look at this relationship, if they were enantiomers, the S here, these two stereocenters would be flipped, right? So this is an S, then that would be an R, that's an R, and that would be an S. Only one of them's flipped, right? So this S here stays the same. And so these are not enantiomers of each other because both those things have to change for those to be enantiomers of each other. They're not the same molecule, right? Because if they were the same molecule, those would be the same. Only one changes. That means these are diastereomers. So if two isomers are related by reversing the configuration of some, but not all chiral centers, then the two molecules are diastereomers of each other. If two isomers are related by reversing the configuration of all chiral centers, then these suckers are enantiomers of each other. So, naming is a really good way to help you see this. That's why naming is really important. But I want us to do an example. But naming is the way that I personally use to see if things are diastereomers or not of each other. But let's look at an example. Okay, given the configuration of the isomer of 1-chloro-2,3-dimethylcyclopentane, which is that molecule shown there, draw one of its diastereomers. Okay, and so as you go through this, we need to first figure out how many chiral centers are there. And we can look at this and we can say, okay, there's one chiral center here, one chiral center here, and one chiral center there. Okay, so we have 3 chiral centers. And then it says, to draw a diastereomer, how many chiral centers should have their configurations reversed? And when you draw a diastereomer, we have to reverse the configurations at some, but not all the chiral centers. So some, but not all. Okay, so in this case, we could reverse the configuration at 1 chiral center or at 2 of the chiral centers, but not all 3. So that means that this is one of those problems where people could have different answers. So for example, right, we could come here and we could say, okay, I'm going to reverse it at this one, CH3, but leave that CH3 and the Cl alone. That would be an example of a diastereomer. We could come here and we could say, okay, I'm going to reverse at this CH3. I'm going to reverse at this CH3, but leave this chlorine alone. That would be another diastereomer. We could come here and we could say, okay, I'm going to leave this CH3 alone, right? But reverse this CH3, and this Cl. Okay. And so you can have, there would be lots of different answers to this if I were to ask you that. Now, if I ask you a different question, if I asked you to draw the enantiomer of this, that means that you need to reverse all of them. So the enantiomer would look like this. Give yourself more room than I gave myself. And here you can see I've reversed all of them. So different answers, as long as you're not asked for the enantiomer, there's only going to be one enantiomer. So let's look at some strategies for how to draw all the stereoisomers of a molecule with chiral centers. When we do this, you can get a new confirmational configurational isomer for each inversion of a tetrahedral stereocenters configuration. And so the number of configurational isomers that can exist can double with the addition of a chiral center, right? And so basically what this is saying is, hey, look, for every configuration, you're going to have an R and S enantiomer, okay? And the opposite configurations aren't superimposable. So whenever a chiral center's configurations are reversed, there's a potential for generating a distinct stereoisomer. So if you just have one stereoisomer, you can have R and S. But let's say you have two chiral centers. With two chiral centers, you could have RR, you could have RS, you could have SR, right? And then you can have SS. So there's a lot of different options here, right? And obviously this would be the enantiomer of this, and these two would be enantiomers of each other. But this one and this one would be diastereomers, and this one would be diastereomers, and this one would be diastereomers, and this one and that one would be diastereomers. So we end up with some diastereomer situations here. And so what we can say then is the maximum number of configurational isomers that can exist for a molecule within chiral centers is 2 raised to the n, okay? Where n here equals the number of chiral centers, okay? Now that's a maximum because depending on the symmetry of the molecules, you could end up with something being meso. So don't forget that if there's a center of symmetry, that's a meso compound, okay? So we love numbers here. So here is our method for how we're going to determine this. All right, if it broke up there, you haven't missed anything. I just had to stop the screencast for a second and restart. So we're looking at methods for drawing all the stereoisomers of a given structure. And so when you do this, the first step is you need to identify all the chiral centers. And my suggestion is to keep track of them, is to label the chiral centers with like a 1, a 2, a 3, etc. Then you need to draw the first structure by specifying the configuration at every chiral center. So remember, you need to use the dash wedge notation to specify each configuration. And for the first structure, right, whatever you choose, the choice of configuration doesn't matter. Then you need to draw the second structure by reversing the configuration only at one chiral center. So like, for example, the chiral center 1. Then you need to draw the next 2 structures by reversing the configurations at the chiral centers, chiral center 2. And then you need to continue to repeat this until you draw everything. And make sure as you continue this pattern, the number of structures will double each time. And then, of course, you want to look for anything that's redundant and omit those. So let's do an example of this. So here is 2,3-dibromo-4-methylhexane. And you can see that I have 1, 2, 3 chiral centers. Now, one of the things that I like to do is figure out how many possible configurational isomers I'm going to have. So I take you know, we're going to go 2 to the nth, where the n is the number of configurations that we have, and we have 3 here, our chiral centers. So 2 to the third gives us 8 possible configurations, right? So that's what we could possibly have. Then we're going to go through and we are going to draw these. So I have another slide here for you, and we can go over to that slide, but I think I'm just going to work down for this. So here's kind of step 2 through 5. So here's step 2 is I'm just going to draw one, and I am going to draw all of the dashed or the hatched wedges. Again, if there was a jump there, I had to pause the screencast just briefly. All right, so I chose to do all the wedges there. Now, I'm going to go to step 3, and I'm basically only going to reverse one of the configurations. So, like, that was step 2, right? Here is going to be step 3. And so at step 3, I'm just going to reverse one of these. So I'm going to leave this here, and I'm going to leave this one here as BR, and I'm going to come in here, and I'm just going to reverse one. And that is a diastereomer, right? Then I'm going to go to step 4, and I'm going to reverse and do basically reverse the second one of A, okay? And so 2, 3, 4, 5. There's that one. 1, 2, 3, 4, 5. BR. But then I'm going to leave this one alone. Okay. And then I'm going to reverse the second one, the step 3, right? So look, if I label this as A, and I'll label this as B, and I'll label this as C, right? We're going to have the C is kind of, is where we've moved one from B, and I'm going to look back at A, right? I'm sorry, C is where we've reversed one from A. Now I'm going to look at B, and I'm going to keep this BR the same, but I'm going to reverse this BR, but leave that one the same. So if we compare, we can see that the only thing I've changed is this one from here to here. And then from here to here, the only thing I've changed is that one. Okay, and we're going to call that D. Okay. A, B, C, D. Perfect. Okay, and then I'm going to go to step 5. And on step 5, what I'm going to do is now I'm going to look at this last configuration. So for example, I'm going to leave these two the same and then change that one. So that would be 2, 3, 4. Okay, and we would call, I'm going to call that one E. And then I'm going to call this one F. And I'm going to look and say, all right, I'm going to look at B and only change one, that last configuration. So I'm going to leave the BR there the same and the BR here the same, and then change that one. So EF. And then here, I'm going to keep the BR the same, like C, right? And I'm going to keep that BR the same, but then I'm going to change this to a dash. We'll call that G. And then 1, 2, 3, 4, 5. I'm going to come here and I'm going to change all of them from the first one. So, and then I'm going to call that one H. So when we go back and count, we're going to see there's 1, 2, 3, 4, 5, 6, 7, 8. Then we're going to look and see if there are any redundancies in these, and I don't see that there are. We're also going to look for mesocompounds. So that would be like centers of symmetry. I don't see that there are any centers of symmetry either. So those are our 8 diastereomers for this. So you could have put those here. I just gave you extra room. I just chose to do it on the original one. Now we are in Fischer Projections. If you are going to biochemistry as your next stop in your chemistry journey, you are going to encounter Fischer Projections. So in a study of simple sugars, which we call saccharides, in the late 19th century, Emil Fischer found himself working with several asymmetric carbons, which we know now have chiral centers, and several molecules at a time. And so that led Fischer to develop a quicker and more convenient way to depict the configurations around these chiral centers, and these are now known as Fischer projections. There are 2 conventions for drawing Fischer projections. One is, and kind of the first one here is, at the intersection of a horizontal line and a vertical line, that's going to indicate a carbon. And that carbon is typically asymmetric if there are 4 different groups attached, right? So it still follows those rules. And then the substituents, the kind of second big idea here, is that the substituents on the horizontal bonds point towards you. Okay? And then the substituents on the vertical bonds point away from you. So vertical bonds, right, point away. So kind of back into the plane of the paper. So what we're going to see here, and basically the analogy that we use is it's reminiscent of a bow tie. So you've got these Z and X here are on this horizontal line. That's going to point towards you like a bow tie would. So those are coming towards you, right? So this is Z and that is X. And then you can see here the W and the Y are pointing back. And so that's the convention that we see from these Fischer projections. And those are used tremendously in biochemistry. So there's a few things to be aware of. If you exchange any 2 substituents on an asymmetric carbon in a Fischer projection, it gives the opposite stereochemical configuration, just like we saw with doing kind of dash and wedges. If you have the mirror image of a Fischer projection, right, that's going to be the opposite stereochemical configuration, just like how we saw before. But here is something that's kind of different. If you rotate a Fischer projection 90 degrees in the plane of the page, it gives you the opposite stereochemical configuration, and that was different. So basically what this is saying is, hey, look, so these 2 are nothing different than what we did before, but this is unique to Fischer projections. And so what we're saying here is, hey, look, if you take this guy right here and you move him over just 90 degrees, right, where now the W and the Y are kind of coming towards you and the Z and the X are coming back, these guys are not superimposable. And so you have made the enantiomer, okay? So the convenience of Fischer projections is really evident when we have multiple asymmetric carbons that exist in the same molecule. And this is what you see in simple sugars. So these are simple sugars. As we're looking at this, you can see we have D-allose, D-glucose, and L-glucose. We've got molecules with 6 adjacent carbons. So 1, 2, 3, 4, 5, 6. All of these has 6 carbons. Notice that 2 carbons, this one here and this one here, are asymmetric, and they are not represented with those perpendicular lines. That's not always the case, but it's pretty easy to identify these are not chiral centers, because what we see here is that this is not going to have 4 different bonds. It's got a double bond, and 2 of these substituents are the same here. Okay, so when we look at this, we are going to see here that D-glucose has the same connectivity as D-allose. Based on their Fischer projections, though, they're diastereomers of each other, not enantiomers, because their stereochemical configurations are opposite and only one of the 4 asymmetric centers, right? So these 2 guys right here are opposite of each other, and so that means those are diastereomers. We have, they are opposite of each other at just one configuration, we have a more specific term that's called an epimer. So if they're opposite of each other at just one configuration, that's called an epimer. Now, I want you to also look here between D-glucose and L-glucose. These guys are enantiomers of each other because we can see they're the mirror images. Each one of these is switched at every chiral carbon. So those are non-superimposable. Now, sometimes you're going to have to go from Fischer projections to the R and S designation. And so these are pretty straightforward using Fischer projections. We can see the priorities have already been established here for us. And so if we go 1, 2, and remember we can draw past a 4, but not a 3. 1, 2, 3, and it's counterclockwise. But, and there might have been a jump there, I had to stop it for just a second. But while these are counterclockwise here, the 4th priority points away from you, okay? So if the 4th priority is on this horizontal line pointing away from you, and we go like this, right? Then you flip it and it's clockwise, okay? And so that's R. Different books treat this different ways, but basically, if you have your 4th priority on this horizontal, instead of saying, hey, look, that's S, you switch it and say it's R. And I know that's confusing, and I apologize on behalf of all the scientists out there. Now, here is one of the things that you need to be aware of, is that sometimes you are going to have to convert between the Fischer projection and a zigzag conformation. So this is our zigzag conformation, and we can convert to a Fischer projection. And so some of the things that you need to think about, right, is you can see, okay, here's our chain of carbons, and we have numbers here, 1, 2, 3, 4, 5, and you can see the numbers here, but we have 3 stereocenters. And so the question is, well, on which side does the OH go and the OH go over here? And so when you go through and do this, right, for each stereoisomer with a horizontal bond pointing towards us, you need to add the substituent on the left and the right of the Fischer projection as they appear in the molecular model. So sorry, there was a siren in the neighborhood and I got distracted. So let me go back. So if it skipped a little bit there, that's what was going on. Okay, so what we mean by this is, look, there's 2 ways we can look at this. This is asymmetric at a peak. And what that's talking about is, if you have a zigzag configuration, that's a peak. And that is a valley. And when we look at these, they're going to point different ways. So for example, we have this peak and there's an X on a solid wedge and a Y on a dashed wedge. And here's a valley, and there's the solid wedge, and there's the dashed wedge, okay? This end here becomes the top of the configuration, the W there and the W there. And so what we find is that if it's at a peak here, it goes on the left side, on a wedge. So peak and wedge, left side. Valley and wedge goes on the right side. Now, I could have just as easily said, hey, look, if it's a peak and a dash, right, it's going to go here on the right side. And if it's in a valley and it's in a peak, a dash here, right, then it's going to go on the left side. Choose one to know, right? Choose one, because the other thing is just going to go on the other side, okay? So it depends on if it's at that kind of peak and wedge. So let's look at that first example again. Right? And so we see here, this is what we consider to be a peak. And we notice that this is a solid wedge. And so it is on a peak at a wedge. And so it's going to come over here on the left side. Then this is at a peak at a valley. So it'll be on the right side. And then this is at a dash. So not a wedge, but a dash. And so at a peak, and it'll also be on this side here. So that's how you can convert from the zigzag configurations to the Fischer configurations here. Now, if you need to convert back, right? So we look here and we have a Fischer configuration and we want to convert to a zigzag configuration. We've made the zigzags here as the carbon chain here. And the question is, where do we put the H's and where do we put the OH's? Well, when you look, you want to see, is this at a peak or a valley? So number 2 here is at a peak and number 3 is at a valley. And so when we look at this, right, and we say, okay, this OH is on the right, that means it's going to appear on the dashed wedge there. So we have NC, boop, 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 OH. And so we are going to see this on the dashed wedge there. Now, I'm not going to show the solid wedge. That is a hydrogen. You don't have to show it. Some books will and some books won't. It just kind of depends. Then we're going to look and we're going to say, okay, the OH is over here on the left, but now we're at a valley. And so if it's on the left and this is going to be a valley, then the OH is here going to be also on a dash. Okay, and so that's what we're going to see. So we can go back and forth between both of those. And you can also see it, all of that written out for you here. The best way to learn this is to practice it. So we have practice problems in the book. We also, and they of course will be at the end of the syllabus with answers in the solutions manual. So my suggestion here is if this seems really confusing, please practice it and come see me and ask questions in my office.